Hello, this is Jack Jackson. Today we're going to be talking about logarithmic functions. So we're going to be introducing this concept. Logarithmic functions turn out to be the inverse of exponential functions. So they are exponential relations in a way, but they're just backwards. So we remember that exponential functions are one-to-one functions, so their inverses must also be one-to-one functions. And so we're going to explore the properties of their inverse functions, which are logarithmic functions. Okay. Now, in the notes here, you're going to be sure, if you print these notes out, be sure you work the exercises that are there before you turn the page. And as you're going through this video, be sure that you work these exercises when I ask you to before you move on. The solutions are here, so you can use this to check them, but you're going to learn a lot more from this if you try to do the work when I ask you to do it. So recall in general that the inverse of a relation is found by switching the ordered pairs of the original relation. So if 0, 1 is on the original, then 1, 0 is on the inverse. In the formula, this amounts to switching the x and y. So also recall that geometrically this amounts to reflecting the graph over the line y equals x. We covered this earlier. So let us apply these results to some exponential functions to find their inverses. And we're going to start with the original function y equals b to the x, just a real basic exponential for a base bigger than 1. So our first example, we're going to do this with a base of 2. So here's what we're going to do. We're going to take this function f of x equals 2 to the x, or just y equals 2 to the x. So first of all, what's the formula for the inverse relation? And then you want to complete a table, okay? And just like we did this back in the inverse relations, in fact we probably did this same problem back in the inverse relation, you're going to use the formula, the blue formula for the original function, which is an exponential, to fill out the y's. And then you're going to find the corresponding points on the inverse. Remember, the corresponding points will just have the x and y switched. Then you're going to take these points here and use them to help you draw graphs of both the original exponential, which we should be pretty good at by now, and then also the inverse, which is going to be, we're going to call it a logarithmic equation, and we'll explain that a little bit more in a minute. Okay? And then let's describe the characteristics we see. You'll write the formula in the first blank here and talk about the domain, range, direction, like increasing, decreasing, constant. Is it a function or not? Is it one-to-one function or not? Concave up, concave down, or linear. Any vertical, horizontal asymptotes, and then the x and y intercepts, if it has any. None might be an appropriate response. Okay? So go ahead and work through this. Hopefully you've got a printout of this that you can work through as well. And you can do that now. So press pause now. Okay, so let's take a look at this and work out the solutions. Well, first of all, the equation is simply, if this original is y equals 2 to the x, the new one is just x equals 2 to the y. And by the way, I'm going to color code things here. So blue is going to be the original exponential, and the red logarithmic function is going to be in red. Okay? So let's fill out the table here. So 2 to the 1 is 2. 2 squared is 4. 2 to the third is 8. 16 here. Going the other way, we're going to take a half of it. So half of 2 is 1. 2 to the negative 1 is a half, or 0.5. 2 to the negative 2 is 1/4, or 0.25. 2 to the negative 3 is 1/8. That's 0.125. And 2 to the negative 4 is 1/2 to the 4th. That's 1/16, which is 0.0625. Let me format that just a little bit better. And so now what we end up doing here, let's see, let's do a little bit of cleaning up here. is we want to take these and we want to simply reverse the x and y coordinates. Okay? So everywhere you have a y here, that's going to be an x here, and everywhere there's an x here, that's going to be a y over here. Okay, and I'll make these red for the new function. Now let's graph these. Actually, I already have it graphed in Graphmatica. And in Graphmatica, I just typed in y equals 2 to the x power. In fact, let me go ahead and write that as y equals 2 to the power x. And this is the blue one. Okay. And so that's the blue one here. Let's see if I can put that right on top of the graph. Okay, so that's this one right here. And then the inverse is going to be just switch x and y. So it's x equals 2 to the y. Now we're going to see in a minute that we can rewrite this, solve for y, as y equals log base 2 of x. Base 2. And all of this, either way we write it, is the red logarithmic function. Okay, and you can see that there. Notice that in general, anytime you have inverse relations, it just flips over the line y equals x, which I have in green. So I just got that for reference. If I had this on a piece of paper and folded it on that line, that green line, the blue and the red would land right on top of each other. So notice some key points here, some of the ones from our table above. 0, 1 is on the blue one, so 1, 0 is on the red on its inverse. 1, 2 is on the blue original, so 2, 1 is on the inverse. 2, 4 is on the original, so 4, 2 is over here on the inverse. The original has 3, 8 right there, so this one should have 8, 3, and you can see it there. Right almost off the screen here is 4, 16 right there, so this should have 16, 4. Okay. 5, 32 is off screen, and 32, 5 is off the screen here. Okay, let's about some with negative x's on the blue one. On the original, negative 1, 1/2 is here, so this one has 1/2, negative 1. This one has negative 2, 1/4, so this has 1/4, negative 2. The blue one, the original, has negative 3, 1/8, so this has 1/8, negative 3 right there. So you see as you go out to the left, the y values are approaching 0 on the blue original exponential function. So notice the exponential has a horizontal asymptote of y equals 0, the x-axis, whereas the red one has a vertical asymptote of x equals 0, the y-axis. So if we summarize some of these properties, we should be able to summarize this. So here is the function. The domain of the exponential, as we've studied before, is all reals, and the range is the positive, 0 to infinity. Remember, the domain range, you're just going to switch. So the domain of a logarithmic function is 0 to infinity, and the range is all reals. So notice that you cannot take a logarithm of a negative number, and you cannot take a logarithm of a 0. Logarithms are undefined for those. Okay. They're both increasing functions, which makes sense. If one increases, the other is going to increase. On the blue one, increasing x increases y, so that means on the red one, increasing y increases x increases y. One increases, so does the other, so that's an increasing function either way you go. Notice that if it's increasing, that by necessity makes it 1-to-1 function, makes it a function and 1-to-1. So that means the inverse is also going to be a one-to-one function. In particular, it's going to be a function, which means you can solve for y. So we have x equals b to the y power, but we should be able to solve for y. Well, we can't do this unless we introduce this different notation called a logarithmic notation. And the notation is x equals b to the y means exactly the same thing as y equals log base b of x. We'll go back over that again in just a minute. And the asymptote, so this has a horizontal asymptote of y equals 0 on the left. Okay. But this other one is going to have a vertical asymptote of x equals 0. Okay, and it happens to be on the right side of the axis. So if you look at it here, this is on the right side of the axis because x has to be positive, but it's pointing down. Okay, pointing down on the right side. This one's pointing to the left above the axis. Notice that the blue one does not cross the x-axis, does not cross its asymptote, and so it has no x-intercept, but it does have a y-intercept of 0, 1. Well, when you reverse that, 0, 1 becomes 1, 0, so that becomes an x-intercept, but now it doesn't. Now the red one doesn't have a y-intercept. It doesn't cross the y-axis. So once again, notice that x equals b to the y is actually a function, so we should be able to solve for y. So there's no way to do it with the notations that we've done before this section, and so what we do is we introduce a new notation, not really new notation, it's been around for a long time, but new for this course, and that is logarithmic notation. Remember, the word logarithm means exponent or power. Okay? So we rewrite this, solve for the logarithm, solve for the power y. So when we do that, y equals a logarithm, it equals a power, so y is a logarithm. The base is down here, is written as b, that's the same base over here. So the base is the base either place, sort of like Dr. Seuss or a bad rap song, take your pick. And the input here is x. So notice the x is by itself on the left equation, so it can't be the one by itself on the right. It's the y is the one by itself on the right. And of course y is not by itself on the left. So one is solved for x, one is solved for y. These are exactly the same relation. These are the same points, set of points in either way. So it's just like if you said y equals x plus 2 and you said x equals y minus 2. Those are two forms of the same equation. They're actually saying the same thing. They're the same relationship. So these are just two different ways to say the same relationship, and we can take this as our definition of what we mean by logarithmic notation. So when you see this notation on the right, it means the notation on the left. So every logarithmic expression relates to an equivalent exponential expression. The word logarithm is synonymous with the word exponent and power. So logarithms are really just exponents in disguise. And because of this, every time we get a property of exponents, that's going to correspond to a corresponding property of logarithms. And so we're actually going to wait till our next section to do most of these properties. We'll do a couple things in this section, but we'll expand to new properties in our next section. Okay? And eventually you'll need to memorize those properties, and we'll see how they work. But they all boil down to the fact that the word logarithm means exponent. And so again, here's our basic relationship, that x equals b to the y is saying the same thing as y equals log base b of x. So the y, the logarithm, is the y, it is the exponent, it is the power, it is the logarithm. So once again, I'm just kind of saying the same thing again, that the equation is solved for different variables. On the right, the logarithm is y, which is the exponent. In the left expression, the base is the base either place, it is the same. Okay? On the one hand, you use 1 to get y by itself and the other one to get x by itself. So for example, if I say 8 equals 2 to the third power, that's the same thing as saying 3 equals log base 2 of 8. So basically when we write log base 2 of 8 is y, some unknown y, we're saying 2 to the y power is 8. So we're asking 2 to what power is 8? So log base 2 of 8 is saying 2 to what power is 8? And the answer is the power. The answer is the exponent. The answer is the logarithm. Well, in this case it's 3, of course. So let's see if we can apply these basic results in a few examples here. So this first set of exercises here, exercise 2, A, B, C, D, and E, is to rewrite these expressions, which are exponential expressions now, to rewrite them as equivalent logarithmic equations. So let's review real fast. You're going to be using this basic property. Here's an example, and we're taking something that looks like the thing on the left here and rewriting it as like something on the right. So you might want to jot that down and then try these exercises on your own. Go ahead and do this now. Press pause. Okay, now that you're back, hopefully you've done these, and let's see if we can go ahead and work these out. It's a pain. Okay, so I want to rewrite this. Let me get rid of these blanks. Okay, and each case I want to rewrite these as equivalent exponential or logarithms. So which is the logarithm? The log is 2, so 2 equals the logarithm. The base is 3, and so that leaves it must be the logarithm of 9. Or let me just put the 2 on the other side. Okay, let's do the next one. Okay, the base is what? Base is 2. The logarithm is 16. Now the logarithm is 4. 4 is the power. 4 is the logarithm. So that means the 16 must be what goes inside here. Okay, we'll fill in the blanks here. The base is 3. The logarithm is the y, so that goes here. Y equals the logarithm, and that's of 81. By the way, didn't ask us to do this, but what's y? So we're saying 3 to what power is 81, and the answer is 4. Okay. This time the logarithm is base 10. The logarithm is s, so that's over here by itself, and then that leaves must be the v that goes here. Okay, this time the last one, the logarithm, the base is 5, the logarithm is t, so that's the power here, which goes out here, and that leaves must be 12 here. So we're saying 5 to what power is 12? Let's see, 5 to the first power is 5, 5 to the second power is 25. So it's 1 point something because we know that logarithm is going to be a connected continuous function. So it's somewhere in between 1 and 2, but we don't know exactly where it is. We'll talk about how to approximate that a little bit later on. Okay? Alright, the next set of exercises goes exactly backwards from that. Rewrite each of the following, and these start as logarithmic expressions, and we want to rewrite them as exponentials. So you should be able to do these now. Press pause and come back when you think you have answers. Okay, so let's take a look at this and see if we can work out what these are going to be. Well, I usually start with the base. So the base is the base here, the one that's the subscript, so that's 3. And we got to raise that to the power. The power is the logarithm. What is the logarithm? The logarithm is 5. See, the log is equal to 5, so 5 must be the logarithm. What does that leave? That leaves only one more thing to put, 243 on the other side. By the way, notice that that is true. 3 to the 5th power is 243. Okay, and I'm just going to copy this because it gets my format right. My base, though, is 2. My logarithm, my power, is 4. And it should be equal to 16. Is that true? 2 to the 4th, sure enough, that is 16. Down here, the base is 5. The logarithm, the power, is what we're looking for, x, and that must leave 25 here. Now, by the way, what does that make x? That makes x be what? 2. So when we say log base 5 of 25, we're saying 5 to what power is 25? And of course the answer is 2. Okay, the next one, the base is 2. The logarithm, the power, the exponent is y, and that leaves 41 to be out here. 2 to what power is 41? Well, that's going to be harder to say, but let's see, 2 to the 5th power is 32. 2 to the 6th power is 64, so it's somewhere between 5 and 6, 5 point something. Here the base is our e that we use for our compound continuous problems, our exponential base, our standard base. Y is the logarithm, and then 10. So e to what power is 10? Well, e is about 3, so e squared is going to be a little bit less than 3. I mean, e is a little bit less than 3, so e squared is going to be a little bit less than 9. E to the 3rd power is going to be 20 something, so it's probably going to be, well, it is going to be between 2 and 3, but we don't know exactly what. Turns out there's a way to do that one on your calculator pretty easily, and we'll talk about that in a little while, probably in our next video actually. Now, see if you can use this basic idea to actually figure out what these expressions are and simplify your final answer. All of these work out very nicely to a single number that's a nice number. Okay? Press pause now. Okay, now hopefully you've already worked these problems right here. Let's go back and see. So what we want to do is take this, and each one of these we want to figure out what it is. And so what we're doing is we're basically trying to figure out what the power would be. What is the logarithm? What is the power? So 3 to what power is 27? And the answer is 3. And the reason for that, of course, is that when we rewrite this as an exponential, that 3 to the power 3 is 27. The base here, 3, is this 3. This exponent, that logarithm, is the logarithm, the power. Okay, down here we're saying 2 to what power is 32? The answer is 5. So we're saying 2 to the 5th power is 32. So the part I put in parentheses you wouldn't necessarily write down. You could do that in your head. How about the next one? 5 to what power is 125? The answer is 3. 5 to the 3rd power is 125. Alright, so how about the next one? Well, it's 2. Because 7, why? Because 7 to what power is 49? Well, 7 to the 2nd power is 49. And of course, the answer here is just 8, because e to the 8th power is e to the 8th power. So if you can ever get these two bases the same, this cancels out. So another way we could write this one is, think of it like this. Think of the 49 as the 7 square. And then now these two are the same base, so they cancel each other out. So that's another way to think of it. Well, this last thing that we did is something that you can always do with inverse functions. Now remember, to use this notation, f of x and f inverse of x, both the original function and its inverse have to be functions, which means they're both actually one-to-one functions. So if we have f of x equals b to the x and f inverse is log base b of x, those are in fact inverse functions. And one basic thing that we have here is, in general, if you have f inverse of x and then you take the output of that and do f of that, they cancel each other out. So it's like 2 steps forward, 2 steps back, you're right back where you started. and the other one's 2 steps back and then 2 steps forward. One is one way, one's the other, but they still cancel each other out. So like if you add 1, then you subtract 1, you're back where you started. Or if you subtract 1, then add 1, you're back where you started. Or if you multiply by 5 and then divide by 5, they cancel each other out. So exponentials and logarithms cancel each other out in the same way. So if f of x is the exponential b to the x, then f inverse is log base b of x. So we should see x equals f compose f inverse of x. That's f of f inverse of x. F inverse of x is log base b of x, and f of that is b to that power. So it should be that b to the power log base b of x is x. Now, if you look at this, this turns out to be actually kind of obvious when you rewrite it. This is basically an exponential. Think of like x equals b to the u. If you rewrite that, that's log base b of x equals u. But what is u? U is log base b of x. And certainly, I don't think anybody's going to argue with this statement. Log base b of x and log base b of x are the same. So what we're doing is basically taking this, rewriting the base here, the of x, that goes here, and so that means this whole thing becomes the power here. And so those are equivalent. Similarly, if you do it in the other order, f inverse of f of x, f inverse compose f of x, which is f inverse of f of x is b to the x. Take f inverse of that, we're taking log base b of b to the x power. And by the way, I am going to do something here. Okay, whatever. You should have these in parentheses. Sometimes it's acceptable to leave those parentheses out, but I think it makes a lot more sense of what's actually going on if you leave them in. So if we were to rewrite this as an equivalent exponential, that's the base, x is the logarithm, so that makes it the power. That leaves whatever's in here on the other side, and of course you get another statement that's equally true, b to the x equals b to the x. So these are really just saying the same thing in a different order, a different way of writing it. But this gives us a couple of nice properties that we have for exponentials. That we can work with. Okay? So it says if you ever have log base b of x, and that's the power with the base of b, that basically that exponential and logarithm cancel each other out, leaving x. And we've already used this version over here, which actually gets used even more often, which is log base b of b to the x is just x. So we actually use that property right here. Log base 7 of 7 to the second, they cancel each other out, just leaving a 2. Log base e of e to the 8, they cancel each other out, just leave the 8. As long as those bases are the same, they cancel each other out. So basically we've got these properties thus far. F of x equals b to the x and f inverse of x equals log base b of x are inverse functions. Another way to say that is x equals b to the y means the same thing as y equals log base b of x. So in the second line, these are the same relationship, one solved for x and one solved for y, but if you graph this, it'd be the same graph. In the first one, we've actually switched x and y, so this gives you two different graphs, like the red and blue graph that we saw up above. And the next two equations, let me put parentheses here on this other one. Like we should have. Then they cancel each other out is basically what we're saying. So log base b of x first and then b to that power. As long as the bases are the same, everything cancels out, leaving just that original x inside there. And if you take log base b of b to the x power again, the bases are the same, they cancel each other out, leaving that x inside. So see if you can use that property, those properties here, to simplify these expressions here. So I'll give you a chance to work on those on your own, and then we'll come back and check your answers in a minute. Press pause now. Well, let's take a look here and see what we've come up with. Okay. This is, I did this before with a earlier fonts, and it's not liking this. That's why I keep getting those error messages, but no worries, we'll get it fixed as we go along here. Okay, so the question is, can I write, well, let's do the second one first. Notice they're already written as the same base, so they just cancel each other out and leave the 2.5. So the question in this first one is, can I rewrite the 16 as 2 to some power? And if I can, that power is the answer, and the answer is, of course, yes, I can do that. The power is 4. The next one is log base 10, so I need to write this as 10 to a power, and of course I think we can easily see that that is 10 to the third power, so the answer is 3. They cancel each other out. Likewise, here the bases are the same, so they cancel each other out, leaving 2.4. Again, they cancel each other out here, leaving 12.8. Now, look at this one. This is interesting because really it doesn't matter what the base is. 1 can be written as b to what power? The 0 power. So, log base b of 1 is always 0 no matter what the base is. Well, at least for any positive base, which is all we're going to allow. And here's another one. It's nice. If we rewrite, we can rewrite b as b to the first power, so log base b of b is 1. So log base 2 of 2 is 1. Log base 3 of 3 is 1. So a couple of special, so these last two give you some special properties there that it doesn't matter what b is. Now, way back up here at the beginning, when we looked at these, this exercise 1, and we looked at the graph here, we did an example where the base was bigger than 1. And any of them, when the base is bigger than 1, are going to have very similar graph characteristics. These graph characteristics apply in general for an exponential growth function where the base is bigger than 1. And then these characteristics that you see here are going to be the same for the logarithm that goes with it, that's the inverse of it. Now what we're going to do is switch to an exponential decay function. So remember that an exponential decay function is when we have a base less than 1, but positive, so between 0 and 1. So for an example, I'm going to do 1/2 to the x. In other words, y equals 1/2 to the x, or f of x equals 1/2 to the x. And see if we can work this one out like we did the last one, like we did exercise 1. Find the inverse relation just in terms of x and y. You could actually use logarithmic notation here as well, now that you know it. Then we can go along and graph both, and then tell me what you see in terms of the properties here in these examples. Okay? So press pause now. Go back and work this. Press pause now. Okay, well, let's see what we've got here. Okay, 1/2 to the 0 is 1. 1/2 to the 1 is 1/2, which equals 0.5. 1/2 to the second is 1/4, which equals 0.25. 1/2 to the third is 1/8. 1 over 2 to the third, which is 1/8, which is 0.012. 0.125. Let's get a little bit more space here to work this. Let's make that look a little better. Okay. And then we go this way. Let's see, one more down here. 1/16, which is 0.0625. And here we get 2, 4, 8, 16, and next one will be 32, and so forth. Over here, we're just switching the ordered pairs. So whatever was y here is x over here, and whatever is x here is y over here. I'll get the color coding going here. Those are brown. And that should match my graphs I have. The brown one is the logarithm, and the purple one is the exponential. Let me make a note right here. Note, exponential functions have a horizontal asymptote, and logarithmic functions have a vertical asymptote. And this is going to be, let me make that a little bit bigger and bold. Okay, that's going to be true in general, even if we do some transformations like stretching this and sliding it around and so forth. If you remember, when we did that to exponential functions, we always had a horizontal asymptote on one side or the other. Only on one side, but not on both ends, but one end or the other, we always had a horizontal asymptote. So logarithmic functions are going to always have a vertical asymptote somewhere. Notice again, you can see the reflection over the line y equals x. Let's check some points. Here's 0, 1. Here's 1, 1/2, 2, 1/4, 3, 1/8. So instead of 0, 1, this one's going to have 1, 0. Instead of 1/2, 1, this is going to have 1, 1/2. Okay. This one's going to have 1/2, 1. There it is. Instead of 2, 1/4, this is going to have 1/4, 2 right there. Instead of this point here at 3, 1/8, this is going to have a point right here at 1/8, 3. Instead of this one having a point at -1, 2, this one here is going to have one at 2, -1. So if the original one has 2, -2, 4, the inverse is going to have one at 4, -2, and so forth. So what do we see here in the graph, in the table, and so forth? What properties do we see? Okay. So by the way, both are decreasing functions, so I'm going to call them both decay functions, or decreasing functions. I could have said decreasing exponential function. That would have worked too. So again, the basic form is just y equals b to the x. We're not doing any more transformations. We're just choosing a base between 0 and 1. So the inverse would be x equals b to the y. Now, of course, we know that's rewritten as y equals log base b of x. But this time the base is, that's not right. The base should be where? Between 0 and 1. So a base between 0 and 1. Well, many of the characteristics are the same as before. In the purple one, the original exponential decay, remember the domain is all reals and the range is only positives. So again, the logarithm, even whether it's a base bigger than 1 or less than 1, the domain is only positives and the range is all reals. So as long as it's just a basic x inside the parentheses there of the logarithm, remember you can only put in any positive, but only positives. You cannot take a logarithm of a 0. You cannot take a logarithm of a negative. You know, that's another thing that maybe we should make as a big bold statement. Make a couple of big statements here. There's one. We cannot take the logarithm of 0, and we cannot take the logarithm of a negative. These things are undefined. We can take the logarithm of a positive, any positive. Alright, so let's see where we are. Notice that they're decreasing, both of them. They're still both one-to-one functions, and in this case they're both concave up, as you can see from the picture. Concave up, decreasing. In fact, their shapes are very similar. Of course, they're congruent shapes. They're just reflected over the line y equals x. So again, the way to tell them apart, whether it's an exponential or a logarithm, is to find that asymptote. Once you see that horizontal asymptote, that's a good chance that it might be an exponential. And if it's a logarithm, you should be able to see a vertical asymptote somewhere. Even if we slide it around, it's still going to have vertical asymptotes somewhere. So the asymptotes, again, let me emphasize that it's a horizontal asymptote of y equals 0 on the left, whereas this one has a vertical asymptote of x equals 0. It's on the right side of the y-axis, but notice the arrow is pointing the opposite way from before. When the base is bigger than 1, this was down here in this quadrant on the axis, coming close to the axis, and this one was over here. So remember, when we just switch the base to a 1 less than 1, it's kind of like, it could be rewritten with a base bigger than 1, but with a negative x for the power. So this purple one is reflected over the x-axis, y-axis of the 2 to the x that we looked at earlier. And similarly, this brown one here, log base 1/2 of x, is reflected over the x-axis from log base 2 of x. So the x-intercept is still 1, 0 on the logarithm, and it has no y-intercept because the x-intercept doesn't exist on the exponential, and the y-intercept is 0, 1. Okay, so finally the exercise I want you to do here in this section is to open the Geogebra applet transformations of exponential and logarithmic graphs and experiment by manipulating the sliders. In this applet you'll get a graph of a transformed exponential function, and it'll be graphed along with its inverse, which will be reflected over the line y equals x, which will give you a transformed logarithmic function. So you get to see what these look like if we slide them around, or do something else with them, flip them over or whatever. Okay? And so this will give you these different possibilities for exponential and logarithm. And by the way, once again, the key to telling which one's exponential and logarithm is this right here: which one's got a horizontal asymptote and which one's got a vertical. Okay, let's stop there, and you can go on to that applet to finish up here, and then to your homework.